Okay, so this is a related rates question from Active Calculus by Boelkins. This is activity 3.5.3. I've taken little snippets of it and I've put them here in an exercise for us to consider. And so sort of our first thing that we should do, I suppose, is read the question multiple times. So, a television camera is positioned 4,000 feet from the base of a rocket launching pad. The angle of elevation of the camera has to change at the correct rate in order to keep the rocket in sight. Suppose that the rocket speed is 600 feet per second at the instant it has risen 3,000 feet. How fast is the camera's angle of elevation changing at that same moment? All right. So read that through once at least, right? And if you need to, read it through multiple times. Because you won't glean everything necessarily on the first read-through, right? And so how do we approach such a thing? So I think the first step after reading multiple times is to draw multiple pictures, right? And so let's draw multiple pictures. And when I say multiple pictures, I suppose I mean you want to consider different instants in time, different little snapshots in time, including a special time. So different instants in time. So let's go ahead and do that. Let's just sort of imagine the situation as we see it. Right? And so let's draw multiple. And for the sake of our sanity, I'm going to make this, right? We have a camera here that's somewhere on the ground, sort of level with the launch pad. And so over here, there's a launch pad, right? And the rocket has risen a little bit. And I'm not going to, I can't really draw very well, so I'm not going to try to draw these objects. But we have a sort of situation like that, right? And so we have a camera filming the launch pad as the rocket rises, and we want the camera to change its angle to match the rocket as it rises. And so let's see. This is perhaps one possible instant time shortly after the rocket left the ground. I'm going to draw multiple pictures with the same length of base here, because the camera and the launch pad aren't moving, the rocket is rising up, right? And so we have different pictures like this. And in all of them, right, they have the same length of base. The rocket, we can assume that's a right angle because the rocket is rising vertically, and the camera is trying to account for the rocket's rise by changing its angle. All right, so we have multiple pictures. All right, and you want to draw perhaps a representative picture, something that will perhaps capture all the information that we could possibly want. A picture that we're going to label with variables and constants. That's what I mean by a representative picture, right? And so sort of our next step here is to label our representative picture with variables. Let's move this up. Label picture with variables and constants. Right. So what does that look like? Let's see here. So if we read the question again, right, we have, let's see, that the television camera is 4,000 feet. So camera on the left, launch pad on the right, 4,000 feet from the base, right? And if we look at our pictures here, these pictures up above, thinking about what sorts of quantities are changing, what's staying the same, the base is always 4,000 feet. The camera and the launch pad aren't moving. The rocket is rising at a certain rate, right? And the distance between the camera and the rocket is changing over time, all right? And so we need to, for the quantities that are changing over time, we need to come up with variables, and so I'm going to label those in perhaps a different color. Let's say red, right? So here's S, no, let's call this y. I changed my mind. This will be y. And then this distance will be s. Right? So I've just chosen two letters that I like. We also need to, while I'm giving these names as variables, we need to consider them as changing with respect to time. And so since these quantities are changing with respect to time, we should think of them as functions of time. And so I'm going to write of t here in these pictures. Right? And so I have your y of t, s of t. Right? Thinking of that as quantities that change with respect to time. We also need to consider that the angle, which is sort of what we're concerned with, the angle is also changing with respect to time. So that angle, as you can see in the above pictures, this angle that we have to raise the camera at is changing with respect to time. Right? So we label that with variables and constants. Right? And we need to consider our snapshot in time. Right? So let's consider, I'm going to say let t equals t star be the instant in time at which the rocket is 3,000 feet above the launch pad. So I've given this a special name, t equals t star. I've given t star as one particular time, and we're going to draw a picture of that particular time. Right? And so at that particular time, this is still 4,000 feet at the base. We're going to say y of t star, right? Y of t star at that particular time, we said that this is when the rocket is 3,000 feet above the launch pad. And then we have the distance here, s of t star, is, well, perhaps we don't know what that is, right? That's not necessarily what we're looking for, but maybe it's an important piece that will help us in a minute. Okay, so we have these bits of information, and so with these bits of information labeled, right, we should also consider perhaps the other piece of information. The rocket's speed is 600 feet per second, so the rocket is rising at 600 feet per second at this one instant in time, and so at this, this is the snapshot t equals t star at one instant in time, and so we should consider then that information that's rising at 600 feet per second, that rocket is rising at 600 feet per second, we should consider that as dy dt. Maybe it's not constant, so we need to think about evaluating that at the particular instant in time. That information is 600 feet per second, and it's useful to label all the units and keep track of units throughout the problem, I believe. I think that'll be your best bet. Okay? Right. So now we need to think about what is it that, let's see, yeah, so we need to determine our goal. Right. And so to determine our goal, we need to think, okay, so the question was, how fast is the camera's angle of elevation changing at this moment in time, this special moment? And so we need to interpret that, right? I suppose I could also label here, we're talking about the angle. We don't know necessarily what that angle is, but we'll write in theta of t star. And so the question is, how fast is that angle changing? What's the rate of change of this angle? So the question is, d theta dt at that special time is what? Right? Right? And so at that special time, what is the rate of change of that angle? And so we have all the other bits of information, well, we have most of the other bits of information about, let's raise this up so you can see it. And we have the other bits of information that we're going to need to use to help us determine this. Okay? And so after we've determined our goal, right, that's what we want to know, we need to think, all right, we need to relate the variables. We need to think about how to relate the variables. Relate the variables and constants. All right. And so we're going to need to relate theta right? In order to find d theta dt, we're going to need to relate theta to the other quantities within our diagram. And so what can we do? Right? We need to perhaps use some sort of trigonometric function to relate this to the size of this triangle. And there are multiple trig functions for us to consider. So let us think about this as perhaps, I particularly like tangent here, so maybe we consider tangent of theta of t. And we're going to relate not just at t star, but at all particular times t. So tangent of theta of t, thinking as a function of time, is equal to, opposite over adjacent, is equal to y of t divided by 4,000 feet. Right. Okay. So tangent of theta t is equal to y of t over 4,000 feet. And so considering this, right, now that we've got an equation relating our variables and constants, right, now we can differentiate this equation implicitly. With respect to time. And what do we obtain? We obtain, right? And so the derivative, we need to consider this on the left here. We need to consider this a composition of functions, right? Theta of t is my inner function. Tangent of theta is my outer function. And so thinking of the derivative of the outer function, we get secant squared. Using the chain rule, we evaluate it at the inner function, multiplied by the derivative of the inner function. Right? And we can consider this perhaps 1 over 4,000 feet times y of t, if we like. Right? In the sense that perhaps now I can differentiate this as 1 over 4,000 feet, and I'm going to leave the units in there. I think it helps me. Right, times the derivative of y with respect to time. And notice we're not evaluating anything here. We have done this at any time t, not just at t equals t star, our special time. And so let's see, what do we get? Right. So we've differentiated with respect to time, and now at the very end, always at the very end, we need to evaluate each quantity at t equals t star. So we need to consider every quantity changing over time. Theta and y and s are all changing with respect to time. Right. So what do we have here? Right. We get, all right, we don't necessarily know. Let's remind ourselves of what our picture is here. Right. We need to know secant squared of theta of t, so we need to know what secant of theta of t is, right? And so perhaps we don't know what, secant secant of theta of t would perhaps be hypotenuse over adjacent, right? And so if we go ahead and plug in t star, evaluate everything at t star, our special time, then we don't necessarily know what s of t star is yet, but we can figure it out. We don't know the distance between the rocket and the camera, right, necessarily, but we can figure that out. This is actually a 3, 4, 5 right triangle, and so we can perhaps, using the Pythagorean theorem, we can identify that this is 5,000 feet. Right? And so now looking at that picture still, I keep keep moving the notes around, right? What is secant of theta at this special time, right? Secant is hypotenuse divided by adjacent. It's 1 over cosine of theta, right? And so it's 5,000 feet divided by 4,000 feet, right? So secant itself would be 5,000 over 4,000. So we have 5,000 feet divided by 4,000 feet quantity squared. multiplied by d theta dt at the special time. Well, we don't know what that is. That's exactly what we're looking for. We determined up in number 3 that this is the quantity we want to know. We have 1 over 4,000 feet multiplied by dy dt at the special time. We don't know dy dt generally, but we do know that at this one special time, this is 600 feet per second. Right? And so, let's see, we can do some unit cancellation here. Feet divided by feet is 1, and so this is 5 divided by 4 squared. So this is 25 over 16 multiplied by d theta dt at the special time. It's 1 over 4,000 feet times 600 feet per second. And so now I suppose if we multiply both sides, by 16/25, and there are no units attached to that, it's just 16/25. We multiply both sides by that, and what do we obtain? The number multiplied by its reciprocal is 1, and we get d theta dt t equals t star is, and let's see, if we multiply this together, right, there's some, I believe what we end up with is 0.096, and if you keep track of the units, what you're left with is 1 over seconds. All right, so some things to consider. What does this mean, 1 over seconds? That's one thing to consider. What do these units mean? You should always consider what your units mean. The sign here was plus. We have a positive 0.096. We could have ended up with a negative depending on the sort of situation we're looking at. So how do we interpret the sign, right? That's another thing to consider. And then we should also consider writing our results as a sentence, right? So let's see. So 1 over seconds, let's start there. What does that mean? Well, in this instance, we're considering the rate of change of an angle, and radians aren't really a unit to write in here, but the way we should think of this is d theta dt at the special time, 0.096 radians per second. Radians aren't a unit in the same way that feet or meters or degrees Celsius or whatever are units. Right? And so that's how we can interpret this. What does the sign here mean? Why does it mean that we got plus 0.096 instead of negative? Well, this means that the angle, as expected, is increasing over time. If we consider our pictures again, right? Our angle is increasing with respect to time. And so then how could we write this as a sentence? We could say, let's write this as a sentence. At the instant t equals t star, when the rocket is 3,000 feet above the launch pad, the angle that the camera makes with the ground makes with the ground is increasing at a rate of 0.096 radians per second. And that is all of our consideration for this question.